Okay, in this lesson, now we're going to look at how we can differentiate and integrate exponential functions that have bases other than e. And this is going to be very useful because, of course, you're going to see equations that, aren't just e to the x or, natural log of e. In real life, we have bases other than e, so we usually will say a to represent, a number other than e. A could be, 10, a could be 5, it's whatever. And let's first go over some basic examples of how we deal with exponential equations and how it can relate to real life applications that you probably heard of, like half-life, maybe in your bio class or chemistry class. So this is a pretty common scenario that we use this stuff in. So let's first review some of the stuff you may have covered in algebra 1, algebra 2, or pre-cal or something like that. So here we got the half-life of carbon-14 to be about 5,715 years. And we got a sample with 1 gram, and we want to figure out how much is going to be present in 10,000 years. Sometimes you're going to learn that instead of having to create a logarithmic equation where you take the log of 2 expressions, set them equal, use logarithm properties, and all that to solve for something, it's sometimes easier to just use the half-life or 1/2 as a base to solve, for time in this case. So what you can do is write that the amount of carbon-14, or y, will be equal to 1/2 raised to the t power divided by the length of time it takes to get to that 1/2. So the length of time, or the half-life, basically the length of the half-life, which is 5,715. Now, just to give you basic reasoning for how this works is, half-life, represents half the amount. So if we have 1 gram, half the amount of 1 gram is half a gram. So if we want to figure out how long it takes to get half a gram, the reason this works is because that means that t will be 5,715. And if you have 5,715 over 5,715, that's just 1/2 to the 1, which we know is just 1/2. Okay, so using this equation, if you want to figure out how long is going to be present in 10,000, all we have to do is evaluate this equation for 10,000. So if we got t is equal to 10,000, we have 1/2 raised to 10,000 over 5,715. And I advise you to use your calculator for something like this. We got 0.5 raised to the 10,000 divided by 5,715. And we'll get about 0.297. 0.2973 grams will be left after 10,000 years. All right. Now, let's look at a couple more. Let's review a couple more properties of logarithms before we go to before we go through some more examples and before we get to the calculus of this section. So another way we can write a logarithm with a base other than e is by setting it equal to the natural log of x over the natural log of a. And again, we like the natural log because, as we learned in the previous lessons, differentiating and integrating the natural log is super easy because the derivative of e to the x is just e to the x. So if we can write a logarithm in terms of a natural logarithm, that's going to be very useful and makes our calculus lives a lot easier. Now let's remember also how the exponential and logarithmic function relate to one another, and that's them being inverse functions. So the inverse of an exponential function is a logarithm function, and that only holds, if one or the other is true. So if you know it's an exponential, then the inverse is x equals the natural log of y with the base a. Now, you can also use, some of the properties of logarithms. So if you have that base a being raised to the log of x with that same base, this is just equal to x. It's just equal to that logarithm. And when you have, the logarithm of a to the x with the base of a, this just becomes x. And again, that's because you can use the property of logarithms by moving this exponent as a coefficient. So this becomes x times the log of a with the base of a, and the log of base a of a is just 1. So it's just like x times 1, which is just x. Okay, so then some of the first types of equations that you probably learn how to solve, maybe in math 1, math 2, something like that, were exponentials, where you can figure out what the exponent was by recognizing that you can rewrite both of them with the same bases. Now, what if you couldn't? Well, what if you couldn't make them both the same base? Now, in this one you can, but let's pretend that you couldn't. So some of you probably can already know the answer just by looking at it. So just amuse me for a minute, pretend like you don't, because like how do you figure out what the x is? Well, later on, and probably in pre-cal when you learn about logarithms, you realize you could solve these by taking the log of both sides. So you can take the log of 3 to the x and take the log of 1 over 81. Now, this is useful because you can make the base whatever you want, but as long as they're both equal, and the most comfortable or easiest equation to solve is when the base is the same as the base here. So if they make the base 3, this allows us to write these as very simple equations because we can move this x as an exponent, or no, we can move this exponent into a coefficient is what I meant to say. We get x times the log of 3 with a base of 3. This just becomes x times 1, which is just x. And then the left side, or I'm sorry, the right side, you can see that this is basically whatever you raise 3 to get 1 over 81. And again, this is something you maybe want to memorize, memorize, but you've done enough math, probably know that it goes 3, 9, 27, 81. Those are your powers of 3. If you wanted to, you can make this the log of 1 minus the log of 81 and figure out that way. But this is just -4. Because 3 to the -4 is 1 over 81. And that's because 3 to the -4 is 1 over 3 to the 4th, which is just 1 over 81 because 3 to the 4th is 81. Anyways, this just shows that x is -4. And again, you probably already knew that from just mental math, but if you didn't, how would you do that? You can use logarithms to solve it. And let's not forget the other property when you have a logarithm to some base being equal to just some number. Remember that this is just equivalent to the exponential, where 2 is the base, -4 is the exponent, and you have that being equal to x. So 2 to the -4 is equal to x. And then that's just 1 over 2 to the 4th, or 1 over 16. And that's all there is to that.